Confused by names of compounds with metals like iron and copper? You are not alone. Naming compounds with metals that can have multiple charges is a common roadblock. This video offers you a clear and concise guide helping you master the art of representing these tricky compounds. Hi everyone, this is Akhilanand Singh. Welcome to this video on ionic compounds featuring metals with variable oxidation states. Today we will dive into the fascinating world of these special metals. I hope you found my previous videos on covalent compounds and ionic compounds helpful. If you haven't watched them yet, make sure to check them out after this video for a deeper understanding. Let's get started. Transition metals display multiple oxidation states due to the versatility of their electron configurations, particularly in their d and s orbitals. These metals often form ionic compounds by bonding with nonmetals. Naming such compounds requires the use of stock nomenclature, which builds upon standard ionic naming conventions to specify the metal's oxidation state. Before exploring the system of stock nomenclature, let us briefly review the fundamental rules for naming, writing formulas, and drawing Lewis structure of ionic compounds. Rules governing the nomenclature. First cation, then anion. Use IDE suffix with the anion. Do not use prefixes like mono, di, tri, tetra, etc. to mention the number of atoms. Rules governing the chemical formula. Use subscripts to write the number of atoms of cations and anions. The overall charge of an ionic compound must be 0. Rules governing the Lewis structure. Show each ion with charge written as a superscript to clearly indicate its ionic nature. Stock system of nomenclature. Developed by German chemist Alfred Stock, the Stock system uses Roman numerals in parentheses to indicate the metal's oxidation state in a compound, eliminating ambiguity when a metal can form multiple compounds with different oxidation states. Ionic compounds involving iron and chlorine. Iron Fe with atomic number 26 has the electronic configuration argon 3d6 4s2. It commonly forms cations by losing electrons, exhibiting two stable oxidation states +2 and +3. In the +2 state, iron loses 2 electrons from its outermost 4s orbital, resulting in the configuration argon 3d6. In the +3 state, it loses both 4s electrons and one additional electron from the 3d orbital, yielding argon 3d5. Let us see how iron with two different oxidation states combines with chlorine, which has a single oxidation state of -1. Example 1. Ionic compound involving Fe2+ and Cl-. Chemical formula. The Fe2+ cation carries a +2 charge, while the Cl- anion carries a -1 charge. Using the criss-cross method, we can determine the chemical formula of the ionic compound formed. In this method, the numerical charge of the anion becomes the subscript of the cation and the numerical charge of the cation becomes the subscript of the anion, ensuring charge neutrality. For Fe2+ and Cl-, the +2 charge of cation Fe becomes the subscript of the anion Cl and the -1 charge of the anion Cl becomes the subscript of the cation Fe. This results in the formula Fe1Cl2, which can be simplified to FeCl2 as subscripts of 1 are typically omitted. Lewis structure of the compound. We can draw its diagram using the formula. We show the cation Fe+2 in center, flanked by two Cl- anions. We make sure to show the oxidation states of both the ions appropriately in the diagram. Chemical name. The chemical name of the compound is derived using the naming convention for ionic compounds and then applying the stock nomenclature rule on top of it. We write the cation first, then we write the anion with the suffix IDE. The anion in this case is chlorine, which becomes chloride. We avoid prefixes like mono, di, tri, etc. These are used for covalent compounds, not ionic ones like FeCl2. Since iron is a transition metal with variable oxidation states, the stock system requires indicating the oxidation state of the cation in Roman numerals in parentheses. Thus the compound is named iron 2 chloride. Example 2. Ionic compound involving Fe3+ and Cl-. Formula. The Fe3+ cation carries a +3 charge and the Cl- anion carries a -1 charge. Let us determine the chemical formula of the ionic compound formed using the criss-cross method. For Fe3+ and Cl-, the +3 charge of the cation Fe becomes the subscript of the anion Cl. The -1 charge of the anion Cl becomes the subscript of the cation Fe. This results in the formula Fe1Cl3, which can be further simplified to FeCl3 by omitting the subscript 1. Lewis structure. For drawing its Lewis structure, we show the cation Fe plus 3 in center and keep 3 Cl minus anions around it. We also show the charges of the cation and the anions. Chemical name. For deriving the chemical name, we keep in mind two conventions. As per the ionic naming convention, we write the cation followed by the anion with IDE suffix. Abiding by this, the name comes out to be iron chloride. The Stokes system requires indicating the oxidation state in Roman numerals in parentheses after the cation. Applying this rule, the name of the compound becomes iron 3 chloride. Ionic compounds involving iron and oxygen. Now we will see how iron with two different oxidation states, plus 2 and plus 3, combines with oxygen which has a single oxidation state of minus 2. Example 3. Ionic compound involving Fe2 plus and O2 minus. Formula. The Fe2 plus cation has plus 2 charge while the O2 minus anion has minus 2 charge. In this particular case, both the ions have the same charge value. Combining one cation with one anion neutralizes the overall charge of the compound. So the formula of the compound is Fe1O1, which simplifies to FeO. Lewis diagram. We can easily draw its Lewis structure from the formula. For that we show one cation Fe2 plus and one O2 minus anion, one after another, also depicting their charges. Chemical name. As per the ionic naming convention, we write the cation first, followed by the anion with the suffix IDE. This translates to the name iron oxide. Considering the Stokes system, the compound name turns out to be iron 2 oxide. Example 4. Ionic compound involving Fe3 plus and O2 minus. Formula. The Fe3 plus cation bears a plus 3 charge, while the O2 minus anion has a minus 2 charge. Using the crisscross method, we can determine the chemical formula of the ionic compound. For Fe3 plus and O2 minus, the positive 3 charge of the cation Fe becomes the subscript of the anion O, and the negative 2 charge of the anion O becomes the subscript of the cation Fe. This results in the formula Fe2O3. Let us check the correctness of the formula by finding the overall charge of the compound. The total positive charge is the charge of the cation atoms, which is 2 multiplied by plus 3, that is plus 6. Total negative charge is the charge of the anion atoms, which is 3 multiplied by minus 2, which turns out to be minus 6. Combining the total charge of cation and anion, we get 0, so the formula is correct. Lewis structure of the compound Fe2O3. To illustrate the Lewis structure, we place two Fe3 plus cations at the center of the diagram, each with plus 3 charge, and surround them with 3 O2 minus anions, each with minus 2 charge. We ensure the diagram clearly labels the oxidation states. Chemical name. As per the ionic naming convention, the name comes out to be iron oxide. The Stokes system requires indicating the oxidation state of the cation in Roman numerals. Thus, the full name of the compound is iron 3 oxide. Ionic compounds involving copper and sulfur. Copper has an atomic number of 29 with the electronic configuration argon 4s1 3d10. It exhibits two primary oxidation states plus 1 and plus 2, which significantly influence its properties and behavior. In the plus 1 state, copper loses one electron from its 4s orbital, resulting in the configuration of argon 3d10. It also has the ability to lose two electrons, one from the outermost orbital 4s and one from the 3d orbital, to become a cation with plus 2 charge. Let us see how copper with two different oxidation states combines with sulfur, which has a non-metallic oxidation state of minus 2. Example 5. Ionic compound involving Cu plus and S2 minus. Chemical formula. The charges of Cu plus and S2 minus are plus 1 and minus 2 respectively. We can determine the chemical formula using the crisscross method. The positive 1 charge of cation Cu becomes the subscript of anion S, and the negative 2 charge of anion S becomes the subscript of the cation Cu. This results in the formula Cu2S1. Omitting the suffix 1, it can be further simplified to Cu2S. Lewis structure. For drawing the Lewis structure, we show the sulfur anion in center, flanked by two copper cations. We also depict their oxidation states. Chemical name. The chemical name of the compound is derived using the ionic naming conventions as well as the Stokes rule. The name as per basic ionic conventions comes out as copper sulfide. When we apply the Stokes rule on top of it, it turns out to be copper 1 sulfide. The compound Cu2S is commonly known as chalcocite. It appears as a black and a dark grey solid. Example 6. A unique compound involving Cu2 plus and S2 minus. Formula. The copper cation and sulfur anion carry plus 2 and minus 2 charges respectively. Combining one cation with one anion balances the charges and the compound becomes neutral. So the formula is CuS. Structure. In the Lewis structure, we show the cation Cu besides the anion S along with their respective charges. Chemical name. Copper being a metal with variable oxidation states, we construct the chemical name by applying the naming convention for ionic compounds and also the stock naming conventions. Keeping both the conventions in mind, the compound is named copper 2 sulfide. The compound copper 2 sulfide is found as covellite in nature. Covellite is a rare mineral known for its distinctive indigo blue and blue-black color. It is popular among mineral collectors and is used as a gemstone. That's all for this video. In the next one, we will explore ionic compounds with polyatomic ions. Thank you.